the assumption resume the more scientific part. I'm not saying that it's scientific. We'll have some general remarks by people from UFI, from NVIDIA. We'll start with Mark Berger from NVIDIA Corporation.
Okay, cool. Thank you. Hopefully, by the way, I'm Mark Berger from NVIDIA. My role at NVIDIA is to work with software developers, so I spend a lot of time working with our engineers and our solution architects and what I call CUDA ninjas, and Jim and John. It has to be on. Okay, thank you. And Mike Halleck. And so hopefully I'm going to have a little something unique to say today, and it's not going to be a total echo chamber of what you guys have been hearing all along about Klaus. But I'd like to maybe say a little bit of a tribute to Klaus from Silicon Valley. He was an early supporter, and hopefully I can add a little bit of a unique twist here at that time. So today, the NVIDIA platform is a very, very robust platform. The company is really sailing. I don't know if any of you guys watch the stock market. I came in 7 years ago. It was like $20 a share or 25, and now it's up to around 210. The market has finally recognized this kind of performance increase, and Volta is up here somewhere too. OpenACC is now a solid platform. We've ported Gaussian. For those of you guys in the audience, you'll hear an announcement at Supercomputing about Gaussian on P100s, Pascal 100s. We announced K80 support and anyway, too much of a commercial. So, NVIDIA, if you guys have questions, if anybody's doing development, please, you're doing something. I mean, I'm looking for programs that are going to move the needle, that are like a big footprint, or getting in on early technology. So we've been working with Relion and Eric Lindahl and Store Shares for about 2.5 years. So if you guys have some interesting stuff you're doing, please see me, get a card, let's start a communication. But these are pretty mature platforms. We try to do co-design all up from the processor all the way to the application. We try to work with you guys. Everything from embedded controllers that are going into automated cars or drones, these kind of things, all the way up to the cloud, and certainly the gaming platform developed on GeForce, deploy on Tesla, the Matra. But it wasn't always like this. And there was time in the early 2000s, I would say, where, and I guess CUDA was launched here, and before, and you notice I have it a little over to the left, I've been hearing November 2006 is when May, and Klaus kind of linked up, and you guys, maybe John, you were started earlier, I don't know. I put some other things on here, and I have a flavor for machine learning because that's a big deal right now for us, and I've also heard from John that Klaus actually had some neural network papers in the early days, probably during the time that I've heard referred to within NVIDIA as the nuclear winter, the artificial intelligence winter, and so he was another man ahead of his time, as you guys have heard. The first paper here was published on NAMD by Klaus and Jim and others. This is, Fermi, our first HPC GPU. There was a book published by David Kirk and Wen Mei in the 2010 timeframe. Klaus's keynote at GTC was in this. I should have put that on as well. And John was named a CUDA Fellow. And then you guys, you guys have the, you guys have done a few things. Being on the cover of Nature is not too shabby. And then we've had this go on. All the stuff about, to me, the real key value in artificial intelligence and machine learning, deep learning is if you have a boatload of data, you have a huge stack of data, it's great at finding weak signals in that data. The two areas that are really flying the most for us are automated car driving and also healthcare in medical imaging. and even imaging like cytology images, pathology, histology images, etc. All those that are finding not just regions of interest that a biologist is telling the image processing guide, this is a region of interest, put a feature vector in here with color, texture, size, shape, location. But, the system teases out all those weak signals. Okay, so, and then, I'm extrapolating Klaus's vision beyond cells to looking at maybe tissues and organs and so forth. I wouldn't put it past his vision to see that. And combining with machine learning, I think that will be and could be a powerful fulfillment of his vision and the work you guys do here. So that's probably enough about that. So, a couple of the things, everybody's talked about the computational microscope with Klaus. And you guys have done a great job there. I actually come from a bit of a cell biology background. I worked at a biotech that was founded by Ron Vale and Jim Sputich and Larry Goldstein, and it was geared towards muscle biology and motor proteins. And so looking at all the cell, the entire cell, and incorporating additional technologies into what you guys are doing. I haven't heard anybody speak about lattice light sheet, where you're looking at a dozen or more markers in live cell imaging, and you're getting a terabyte of data in live cells in an environmental chamber over the course of a week. Integrating things like that into what you guys are doing. There's an Allen cell that, Paul Allen from Microsoft, he's got a scientific institute in the Seattle area that has a cell visualizer that's pretty exciting. They were in our booth. They're imaging 3D cells and then applying machine learning to actually do extrapolation, inference of what might happen with other kinds of stimuli or environment there. And so I think, there's a whole host of, there's high content screening that most of the pharmaceutical companies do, where you can actually get drug dose response kind of curves by putting different concentrations of drug candidates on disease cell models versus normal cell models. And here, so one of the things that I wanted to cite here is, Klaus has created a lot of, in this environment with you guys, there's a lot of really useful tools. There's VMD that we work closely with. NAMB's history goes way, way back prior to NVIDIA's involvement with you guys. And then this one, certainly, and I know this has about 100,000 or more users. I think NAMB has somewhere in the range of 20,000 users. I don't know what your MDFF has, but I would expect that as you integrate, if you integrate other things, and certainly with cryo-EM in here and FEI microscopes, that's going to be a big deal. I mean, as the Nobel Prize was awarded, I think it's going to be a really big deal. Okay, so the reason I put this up here, and I wanted to say something about this, is you guys have all probably seen Klaus's 2015 Biophysical Society keynote. I'd encourage you to go back, and I uploaded a version of this to see his GTC 2010 keynote, because he goes through 6 examples where he gives a scientific problem, sets up the problem, and then what he does is he actually does a, quote, GPU solution. And he has to speak to people like your parents, okay? From the point of view of, they aren't scientists. Some of these guys are financial programmers doing CUDA for that kind of an industry, or they're marketing people at NVIDIA or whatever. And I think I'm over my time and I should get the hook soon. Is that correct? Okay, so I'll speed it up. I'm not far. But some of the things that I really liked in his presentation were, he talked about ribosomes processing messenger RNA, giving birth to proteins. And I think that makes it more understandable. The other thing he talked about is a crystal, and it's like a picture of a football team standing there, sitting there, and it's totally different than the football team playing on the field, like the protein in the human body and in water, hydrates. So I thought that I actually really, really appreciate people who can take a very difficult concept and be able to dumb it down for people that, that don't have background in that area. Okay, so I loved what Jim said on the first day about dangerous places. And to me, going to bigger and bigger systems and different time scales is definitely the dangerous places that he was going. He also was an evangelist, and I think I'm kind of echoing what everybody has said. This is Klaus at the GTC conference, and you can see how little he is here compared to the big, big screens we have and probably 2,000 people in the audience in 2010. And, you know, he celebrated, he recognized talent. Dave and Jim and John, I think are GPU heroes. I would call them CUDA All-Stars. And Klaus is our CUDA hero. So that's pretty much what I wanted to say, except for one other thing. NVIDIA is going to be making a donation to the Klaus Schulten Memorial Fund. And so, Zahn, I just wanted to let you know that. Okay? So,
the next opening remarks the answers.
Okay, that was an amazingly generous end to a talk that on behalf of the community, I'd like to thank NVIDIA for that again. So, I'm different than many of you because I did not have the privilege to really work with Klaus. I really did not know Klaus that well. I did, of course, know him by reputation for the amazing science he did. We bragged about it at all possible opportunities. The Nature cover that Mark just mentioned, representing work done on blue waters, was one of the examples of the sort of amazing science that Klaus did. He was a friend of NCSA almost from the beginning. He was also a very demanding partner, and I think that was good for both of us. He also shared with us a passion and a commitment for bringing science to public, something else that Mark had just mentioned. And there's an excellent example of both his friendship to NCSA and to the work that we do, and his commitment to the public. And what is my clearest memory of Klaus, that we were hosting a first birthday party reception about blue waters in Washington, D.C., in one of the House office buildings. And naturally, Klaus was one of our 4 speakers, one of 4 that we had brought in. And we had saved Klaus for last because we knew that his presentation would be the great capstone. It would wow everyone as we then went to the mingled reception where the congressional leaders and staffers and other policymakers would get to chat with the scientists who had been working on the system. And Klaus had a just spectacular presentation. This was in the House office building, whose technology apparently dates from the Civil War. And it didn't work. So the beautiful stuff that Klaus had done just didn't work at all. A lot of people would have been flummoxed by this. They would have been challenged by it. Not Klaus. If anything, the talk was even better because his own energy had to replace what he had been planning to use in terms of the animations. There's no other way to describe it. He was magnificent. That really is my clearest memory of him. He was the star, and afterwards, he was of the 4 scientists, he was the one that people sought out because of his passion, the clarity, his descriptions, the vision that he projected. It was really amazing. And so I just wanted to give you that sort of personal recollection that I have in my association with NCSA. Again, Klaus has been a tremendous friend and really pushed us to advance the frontiers of computational science. So his passion, his commitment, his accomplishments, and his generosity were really amazing for NCSA. And we all suffered a great loss with his passing. And NCSA and I join with you in celebrating his life. And, thank you for this opportunity to remember him.
The last opening remark is by Sanjay.
Thank you. Most of you know this. I'm Sanjay Kale, Computer Science Department. I've been here for 32 years, and 26 of them as a collaborator of Klaus Schulten. I want to, you have heard many things about Klaus. Yesterday's opening remarks were amazing, but they also took away, if I was going to take any attempt at describing Klaus and his qualities, well, you heard so much about that. So what I'm going to do instead is to talk about the impact Klaus has had on my career, me and my career. And if I were to follow when May, I would say there's one theorem that I'm going to prove, which is that Klaus has had a great influence and impact on my career. That's the only thing I'm going to talk about and illustrate that bit. Let me go back to 1991. I just had received, I was in that phase when you kind of are getting tenure. It's an anticlimactic phase when someone tells you, yes, you get the department thing, but don't celebrate yet. There is a college, and then there is a campus, and then there is a trustees and so on. And by the time you actually come to the end of the process, it's an anticlimactic end to that. So I was in the middle of that when Klaus walked into my office. I must say that was about the only time he walked into my office. But then he had me hooked, and so I absolutely followed him after that. I was doing this computer science research in those days, working on these n-queens problems and Fibonacci's and so on, which was considered parallel computing in those days by a subset of people. But I had started paying some attention to science and engineering, and Klaus visited me and asked me to be on his proposal that he was working for NIH. And of course, I didn't know much at all about him. He had just arrived here. But then he told me the fact that he and his students had actually built a transputer-based system in their lab, every one of them, grad students, assembling one board and signing it. And that impressed me to no end. It's like, here is someone who was vertically understanding of all the levels of science all the way down to the bits. And I was hooked from that point on. So that collaboration had Bob Steele as a third PI. I took a sabbatical. I decided to learn and read on biophysics a bit. It turned out it wasn't really necessary because what my role was required understanding of the molecular mechanics at the level of high school physics. So that was good enough for me. And then we got early version of NAMD somewhere in 93, 94, around 95. We re-architected that version with Bob, Attila, Jim, and Jim, of course, was a young grad student then, and Mark Nelson and other people. And so this kind of co-developed with my parallel programming effort, abstraction level, something abstraction research that I call Jam++ around that time. And co-design is a word that's thrown around these days quite a bit, but we did co-design at that time. That was definitely a co-design of computer science. So the computer scientist's role in HPC at that time was a little bit of a question. What it was as the computer scientists tended to be somewhat platonic. By that I mean that we got enamored with some beautiful idea and we pursued that, and then we maybe, if we have time, throw it over the fence to the world and say, use it, it's beautiful, and the world didn't care. Alternatively, some computer scientists just turn into programmers for one application or the other, and that doesn't lead to any kind of lasting technology that you apply to a variety of other applications. So what's needed was an application-oriented but computer science-centered research, working on many, many applications, and then developing abstractions that are catered by the needs of one but useful for the others. And this is the philosophy that I ended up developing in those days. In fact, lucky for me, I actually put it down in a position paper in one of these workshops in 1994 with the title Application-Oriented and Computer Science-Centered Research. And this, while I'm coming to where it connects, but basically through Klaus and through these initial grants, I was introduced to many celebrities in the field, many senior scientists and so on. And so, of course, them being very, very famous and very reputed scientists that have nothing left to prove, they were blunt if I asked them a question. So I asked a question, what do you think about the role of a computer scientist? And basically I was told those words, I take a dim view of the role of computer scientists here. And the reason is that these computer scientists have their own agendas. All right? And so they're not helping us programs done fast, they just have developing their own agenda in computer science. And I thought we should have our own agenda, but at the same time we should not be just doing this platonic pursuit of that agenda, but it should be connected with real applications. So it helped me really refine my goals in that period, and that interdisciplinary research, which everyone extols, but it's really a hard path. Those of you know me know that the NAMD development years were exciting for me, but professionally they were tough years. Within your own discipline, for most people, interdisciplinary work doesn't count. And scientists and engineers may think of you just as a programmer, like that I said on the previous slide. And so we need a recognition for computer science research as legitimate research, and Klaus gave me that respect and that role. As a PI, as a co-PI, as a collaborator, Klaus encouraged that computer science research and saw how I needed to develop that agenda at the same time that it was impacting NAMD. So this, I think, is the biggest impact. I'm not going to, this is a nostalgia slide, but it's strange how I keep using that slide in real presentations even today. This is Jim's PhD thesis work. And so, alright, so around that time also for NAMD we came up with a design that turns out to be highly scalable because it applied some ideas like isoefficiency and so on from computer science and came up with some ideas that now are, in my view, the blue matter and what went in Desmond, what in Mark Smith's work are in a sense presaged, were actually there in this work to some extent. And so that idea then, the NAMD parallel structure, done in 93 to 95, if you look down here, the quote is from some write-up, say, we are developing the NAMD project, for instance, on a cluster of 12 HP 735/125 workstations connected with an ATM. Most of you don't think of ATM as anything but the machine where you get money, but it was actually a network in those days. And so, when that same parallel structure has survived until today, running on largest machines of the day, and so that to me, that synergy between developing NAMD and developing my own parallel programming research, that was the biggest thing that we got from this collaboration. So all of these computer science innovation abstractions were triggered by and encouraged by Klaus and the collaboration I had with him. So I thought I should list one thing that I learned from Klaus. I'm going to make a list, but I thought I'll focus on one, going by Klaus's dictum of keeping things simple and not explaining. Well, one of these things was deep capability simulations before their time. People criticize this. It's like, why are you doing this 5 million atom virus which just wiggles for a few nanoseconds and doesn't do anything? Well, it turns out we develop those capabilities ahead of time. When the time comes when the computers are fast enough and large enough, you have developed the parallel simulation capabilities. You can do the HIV virus code when the time comes with this technology and the knowledge. And so this is going deep into something and into a territory and establishing all the problems and solving them ahead of time was one very useful lesson. So the highlight of my collaboration with him was 5 years ago at Supercomputing. We both got the Sydney Fernbach Award. I just want to take a minute, if you have it, to play a video from that, and then I will conclude with just some concluding thoughts. Let's see, I suppose there is a way of escaping this. Hopefully the sound will play, we'll see.
The Sydney Fernbach Award honors the memory of one of the pioneers in the development and application of high-performance computers for the solution of large computational problems. Established in 1992 by the IEEE Computer Society Board of Governors, the award and $2,000 honorarium is given to an individual in recognition of outstanding and innovative contributions in the application of high-performance computers. The 2012 IEEE Computer Society Sidney Fernbach Award is presented to Klaus Schulten and Laxmikant Sanjay Kale for outstanding contributions to the development of widely used parallel software for large biomolecular systems simulation. Klaus Schulten, the Swanland Professor of Physics at Illinois, directs the Center for Biomolecular Modeling and co-directs the Center for Physics of Living Cells. His research, focused on molecular assembly and cooperation in biological cells, requires large-scale computing, and he was the first to demonstrate that parallel computers can be used to solve the classical many-body problem in biomolecular modeling. His group's software for molecular graphics, BMD, and molecular modeling, NAMD, are used by researchers worldwide on platforms ranging from desktop machines to supercomputers. Presently, his group is developing a new computational method that assists biologists in solving the structures of the very large macromolecular complexes forming the machinery of living cells. Sanjay Kale is a professor of computing who focuses on enhancing performance and productivity via adaptive runtime systems.
So you have to imagine this, at supercomputing, a place where 15,000 people were there. This thing was like a 30-foot by 100-foot wide screen, and it was just amazing. I would say, and Klaus was responsible for getting me there. So that was a very proud moment for me. You can kind of get the scale of things from this. I just want to conclude with a couple of points. That my career, as I said, was strongly influenced and impacted by Klaus Schulten. 26 years ago, I came to two roads. I took the one that represented interdisciplinary research. And of course, it has made all the difference. Of course, it has gotten me the career that I have now. But those of you who understand Klaus will understand that there was no fork. Klaus was standing on one road, and his magnetism, his charisma meant that I would go on that road. And thank you, Klaus.
We will start the session, this third session, and the first speaker is Hopkins from the Beckman Institute for biophysical chemistry in Bermen. And so this morning we'll talk about what the mechanistic understanding of ribosomal.
All right. Good morning, and many thanks for joining in. It's a tremendous pleasure and honor to be here on this stage in this building, starting the session this morning. And I should also say right away, I'm really proud and happy to be considered part of the family here, so thank you for that. I show this building not because that's where I come from, but because that was also the home of Sam and Klaus for a while in Göttingen. And a lot of hills and green trees. A nice place. That was before Sam and Klaus moved to Munich. And I'd like to start my lecture with just one anecdote, and I would like to finish it with one. Sorry, Sam, that will be a bit repetitive to what I said to Munich, but all the others haven't heard that, so I probably want to share it again here. I had the immense privilege to have Klaus as a teacher also, and when I was a student at Technical University of Munich, and he taught theoretically physics courses, mechanics, stuff like that, that were like generalized coordinates, Hamiltonian mechanics, and so on. And the lecture started at 9. Typically, Klaus, we have heard this style of work already about yesterday, prepared the lecture more or less deep into the night. And appeared perfectly prepared next morning. So was it this time also, except that when he stood in front of the desk, he realized that his notes he had prepared were all fine and nice, but at home. So he really pulled off a lecture, 90 minutes lecture of that stuff, out of his mind, improvising, but also, of course, remembering what he was preparing, but completely without any notes, on the board, without a single flaw. Highly systematic, step by step, without a single flaw, 90 minutes of that stuff. And I should really say that impressed me a lot. That was a level of mathematical skill which I have never seen before in real life. And that, I think, also says something about one side of Klaus. He clearly was one of the strongest in the field, which I didn't realize at that point, of course. So that's one anecdote I wanted to start with. I also want to put a bit into perspective, specifically as NVIDIA has been mentioned, and also the transputers, which started much of it in the early 90s. I would like to also acknowledge that Helmut Gropp played an important role also in carrying out these single molecule experiments. That was the quality of the data at that time. Sorry for showing that again. It was really the first time people were able to measure the force which is required to pull apart a molecule. And that really got me hooked, so that was completely impressive. And he called me up in the office and they were measuring that. Couldn't you just do the same thing in the simulation? And that started a lot of things. Parallel also with Klaus. And so just to give an idea, that is how that looked at the time. Just 1 or 2 nanoseconds of simulation, so we had to pull really fast in order to, but that was the advantage, right? We could pull fast. We just didn't have to wait, and if something happened spontaneously in the simulation, drink a cup of coffee and return 100 years later. We could just accelerate things by pulling. That was one of the things which I really love. And second thing is, and that goes through the whole field, I think, also of Klaus' research, we could calculate things which could be measured and directly compare. There was one drawback at the time, and I also show that to illustrate this. So that is the force which is measured for this complex rupture as a function of how fast you pull the loading rate. And that's the experimental side here, that is Hermann's data, and that was our data from the simulation side. So fast we had to pull, like 5 or 6 orders of magnitude faster than the fastest the AFM people could do, limited by the resonance frequency of, at that time, quite pretty large cantilever and stuff like that. And so there was a big gap, and you would probably agree that it's a bit hard to really say whether these two data agree or not. At that time we put it on a linear scale, so the gap doesn't look that bad, but in any case, that was the situation. And I'm just showing that to illustrate that since then, I think the field advanced tremendously thanks to algorithmic and hardware advances driven forward in Klaus' group. And this is the situation which we have here. This is unpublished data, but we just managed, in fact, to close the gap completely, even to the point that we have now 1 order of magnitude overlap. So here the blue dots are the triangles are the experimental data by Simon Scheuring at that time, and the green squares are our simulation data, and we have really an overlap of 1 order of magnitude now, without any fitting parameters. So this is just simulation with an off-field force field, and we get these nice agreements. I think that's also really impressive for both sides. And just on top of that, a very simple model, that's the red stuff, based on diffusion in a simple one-dimensional free energy landscape, allows us then to extract information on the energy landscape, to extract, for example, the 2 steps here which give rise to this curved line, etc., etc. So, which is also one thing I think I learned from Klaus. Don't just do the simulations and that's it, but try to understand the underlying physics in terms of simple models too. And that's That makes all the fun. So in contrast to where we started off now, each point here is really a whole bunch of simulations, which gives also access to the distribution of forces, which then again can be nicely compared to experiment. And also Klaus has contributed quite a bit to the theory of the structure processes. But the main topic I would like to go into now is, in my mind, a wonderful machine, which also Klaus has worked a lot on over the past, I think, 10 years or so, is that true? Biologists consider this a rock-solid block, a ribosome, but as you can see already here, it's far from being rock-solid. It's really a highly dynamic machine, and that attracts us to look at, have a closer look into that. And just because I might run out of time at the end, let me just acknowledge the people in my department who did this work. Andrea, Lars, and Michael mostly, which I will be sharing with you now in the next 15 minutes. So I think I don't need to really expand much on the ribosome. It was already said. Nice wording. It gives birth to proteins here. So the proteins are synthesized right here at the active site here. Amino acid by amino acid, and then kind of pushed through this tunnel here where upon exit they fall into the native structure, hopefully, maybe assisted by some chaperones. And the amino acids are delivered by tRNA. Two of them are seen here in the A and the P binding site. E is the empty binding site here. So that's the classic configuration. And actually the tRNA encode the genetic code in that they carry just the right amino acid here at that point, which fits to the triple codon on the other side, which base pairs then to the triple here on the messenger RNA, which is kind of the mother tape carrying the information. And so the cycle goes like tRNA arriving here, being meshed here, delivering the amino acid, moving over to the P site, then to the E site, and leaving the ribosome, while the messenger RNA moves by 3 base pairs forward. So that's the synthesis cycle, which we wanted to have a closer look. And it came at that time quite handy that Ulrich and also Roland Beckman, they advanced cryo quite a bit at that time, and I think Holger was the first who really was able to sort the configurations of the ribosome into, I think, up to 40 different configurations, which are actually the ones which I have shown you before here in this movie. So this is not molecular dynamics. These are the 40 different main 12 of the 40 different configurations which Ulrich was able to capture with cryo-EM at that time. And what we did is we built atomic normals into each of them such that we were able to carry out molecular dynamic simulations on each of those. So if you see this, that would be kind of the coarse, low resolution, low time resolution picture, which covers the whole cycle. And from each of those frames, we spawned molecular dynamic simulations to learn about the high time resolution dynamics. I should also say right away that this sequence of images appears like a movie, but it's not. It is just the images which are drawn from an equilibrium distribution by cryo-EM, a Boltzmann distribution if you wish, of the shock freezing, sorted according to similarity. So there is no time information. It's a statistical ensemble without any time information. And it was just sorted according to structural similarity. No time in that. And the question is, of course, is that a realistic image in terms of what actually is the right sequence of states, in terms of Markov states, one following each other, or not? What is the right sequence? So that was the one open question which we wanted to address at that time. Another question we wanted to address is the question of cause and effect. So, for example, you might see this blue L1 stalk, as it is called. It seems to really grab the green tRNA here and kind of draw it along. But is that true? We don't know just from the images, because it could equally well be the tRNA being the active agent just pushing the L1 stalk along out of its way. It could also be that there's a third agent which drives synchronously both of them. So the cause and effect, that is something which I think our field by molecular dynamic simulations can reveal, and which just pictures alone, be it X-ray or cryo-EM or NMR, cannot so easily reveal. So that was also a reason to set up these kind of simulations. So those were one of the first simulations we were able to carry out, 100 nanoseconds, pretty short, right? Today's standards. but of each of those states. And if you look at it, rather boring. Not much is happening here. But I hope to convince you that we can indeed extract quite a bit of information. And one of it is, in fact, information on kinetics rates. And this I would like to go a little bit into. We heard yesterday already about kind of Marcus theory type approaches, where barrier heights are extracted from, if you want, harmonic approximations to free energies. We can play the same trick here. So what is shown here, let me guide you briefly through that. That is now the sequence of states again here. So each is one simulation, sometimes two, because there's some substates here. And the bars here, they don't show, these are not error bars, they just show the amount of fluctuation on this configurational coordinate, and on this and this, which we see in a 100 nanosecond simulation. Whereas the configurational coordinate, those are the motions we are interested in. For example, in blue here, the motion of this L1 star, in green, the motion of the P tRNA, and in the pink, purple here is the motion of the A located tRNA here towards the left. So that's what the curves show, plus the corresponding fluctuations. And why are those interesting? Because we can use the histogram of these reaction coordinate fluctuations to come up with in this case I've drawn a one-dimensional model, but we have played the same game in different number of effective dimensions to see whether the results are stable with respect to the choice of reaction coordinate. So in a simple picture that could look like that. One of the fluctuations here as a histogram gives this free energy landscape, and the neighboring state fluctuation gives this one, and the intersection plus a few geometric corrections gives the barrier height, which gives us the simple transitions theory rate estimate. Rough estimate, number of assumptions, but nevertheless it gives us an order of magnitude picture of how fast the intrinsic motions and what the intrinsic rates of these motions are actually. It allows us also to answer the question, or to ask the question, what's the rate limiting step in there? And that's a topic, a theme which will reoccur over and over again. So, what's the result of that kind of analysis? That's summarized here, where we simply classified, because our rate estimates are rather approximate, we classified all the rates we found for the 5 different conformational motions in terms of very fast, like 100 nanoseconds or faster, thick line. Thin line would be slower, few microseconds, maybe up to milliseconds, and no line would be very slow. So in that context, the only thing I want to show you here is that, for example, the rotation of the head with respect to the body, I forgot to mention that as many of you, we can look at it here, will know that the ribosome consists of a large and a small subunit here, and during translocation, they rotate with respect to each other by up to 25% degrees. That's quite a lot. And it was typically thought in the community, because this is the largest motion, it should be the rate limiting motion, which limits actually the speed of translation the ribosome is able to perform. Not so, as this analysis shows, that all the motions here are essentially faster than microseconds, cannot be rate limiting. And this is actually quite a surprise, I will get back to that in a minute, that the motion of these large things sliding against each other is really that fast. That's amazing. What is rate limiting, though, as this analysis tells us, is these barriers here, quite high, and they correspond to the motion of the tRNA from A to P and from P to E. So that's this tRNA translocation across the 3 binding sites, which actually is rate limiting, and that is the outcome of this analysis. In fact, when we looked at in the directions which create these barriers or responsible for these barriers, we find by comparison, which we did a posteriori, that those are the residues which are highly conserved, or nucleotides which are highly conserved in the ribosome, establishing that what we find here has something to do with reality, I would say. All right, one other thing this set of rates allowed us to do is now to ask the question, from all possible n factorial different sequences which you can form from these 12 substates here, and we actually went through all of them with those rates, which one has the largest flux, which one contributes most to the overall translocation cycle? And turns out, quite reassuringly, that it's in fact this sequence here, which has, as I mentioned, been derived just by structural similarity. It is as if I would classify you according to structure, put you in a sequence according to similarity, face or hair color, I don't know what. And then that would give you a sorted list of people sorted against along age. Yeah, that is, in fact, astronomers have done exactly this by the stars. So that also works here, at least in this particular example. So now we know that this is the right sequence of states from the simulations. So that is what we can learn from this kind of fluctuation analysis. And to answer also the question I posed concerning the L1 stock, what's the driving agent, we can calculate, did calculate the free energy between the L1 stock and the tRNA, which move together as a function of their mutual separation. And that's indicated here by, I'm not talking about these dots here, but just by this shaded line here. And the positive slope of this line establishes that indeed the L1 stock is the driving agent pulling the tRNA along and not the other way around. So cause and effect can be sorted out from this kind of analysis. And actually we are currently working through the whole ribosome trying to sort out the whole chain of causal effect, starting from GTP hydrolysis, which is the ultimate driving force for the machine, and ending in the translocation, which I've shown you before. All right, now I mentioned that the rotation of the two subunits against each other, this is really remarkable because the interface of these two subunits is huge. So if you just imagine the ribosome sliced up like an orange, and looking at the interface here and here, what I've colored here are what's called in the field bridges, interaction bridges. Many of them were known, some new we discovered from an analysis of the interaction energies, but there are many, and they are pretty strong, and nevertheless, the two halves rotate against each other. And that is surprising because the high speed of which we even observe this rotation, and even in the simulation, microseconds, implies that the whole interaction energy must be absolutely fine-tuned. There shouldn't be any bump or any energy barrier higher than just a few kcal, because those would be immediately rate limiting, and obviously they are not. And nevertheless, of course, the same interface also controls the overall affinity. You may know that the ribosome assembles upon initiation on the messenger RNA and disassembles later on. So this affinity control is also exerted by a fine-tuned balance of all those interactions. And how that works is a great puzzle. And it's not yet completely solved, but I just wanted to share where we are here. And to illustrate that, I have now a sequence of states, again, these 12 states, where I have colored just the strength of the interaction. Blue very weak, red very strong. And I wanted to see here that when we now walk through the cycles, these interactions change quite a bit. So they're highly dynamic, as you can see here, from pre to post, going back and forth again. So they change quite a bit. And this is summarized in these plots here. So the colors agree here with the position of these interactions. And you can see it falls into two groups mostly. There are very strong interactions which in relative terms don't change so much. So they do the overall work. They keep the whole thing together, more or less. They control their thing. But then there are many, many interactions which are pretty weak, very often more at the periphery rather than in the center. And in relative terms, they change quite a lot. So they, for example, this one is active only here, that one is active only here and here. And it's essentially zero in between. So they change a lot. And we speculate that this is the final control. We really love to speculate, although we weren't able to establish that essentially the whole thing works like the, I don't know what the English term is, the dial of a mechanical washing machine. Yeah? If that turns around, it switches on this motor and then switches off this pump and opens this valve and so on. And we love to speculate, but there's really speculation. We dream of finding out that these interactions do a similar thing in the ribosome, switch on important things during the translocation cycle. We don't know yet, that's an open question. But what you can look at is at least a rough estimate of the interaction. Enthalpy, I should emphasize, So we are not able to calculate through the free energies, but just take the enthalpy as a proxy for it. If we add up all that over the cycle, then you can see that it changes quite a bit of the individual components. For example, this DNA interaction here with the 50s and 30s respectively changes quite a bit, and this comes up. This one, the green interaction, vanishes completely, but if you add it up, then you come up with a relatively flat energy landscape, which indicates indeed that the ribosome is fine-tuned, all those interactions are fine-tuned. And looking into what actually happens in detail at the position of these interactions, we came up with at least two different classes of interactions. One we term, maybe not politically fully correct, monogamic interactions, which maintain their partners, just deform a bit during the sliding of 50s respective to 30s. And then we have interactions which really completely change partner and then go back to the old partner during this interactions. And coloring here, according to the two classes, we find, maybe not too surprisingly, that the more polygamic interactions are more in the periphery, whereas the monogamic ones are the strong ones and more in the center of this mode of rotation. And to give you one example, which really shows how large the conformation and transition is, which is going on here, is here what we would term a pin in the rail mechanism. So just focus on the left column, again going through those interactions. The black dots indicate where actually the strong interactions are seen in the respective state, and you can see that they go from here, this side here, all the way 20 angstrom or more to the other side and back again during the rotation cycle. So many interactions form, rupture and getting rebuilt, and all of that in just a fine-tuned way to keep the energy constant. It's also quite instructive to look at the electrostatics, so there are many charged residues, and what we see over and over happening at the periphery is that an electrostatic energy is fine-tuned by a motion, a concerted motion of the respective amino acids, such that they are more close together when they are opposite charges opposing each other, and similar charges, then they kind of, it's not a passive repelling, but it's really an active steering that things are moved away to not to create too high barriers, and then they go back. And things like that are shown here also in atomic detail during the simulation. All right, now let's switch gears. How much time do I have? 11 minutes. Okay. To antibiotics. So there is one antibiotic which we had a closer look, which was together with Martin Street colleagues, and that is erythromycin, which is the basis actually of many antibiotics which are on the market. And the action of erythromycin is that it binds into the exciton. Now, we have rotated the picture here now. The exciton here goes right to the bottom here, and erythromycin in red is just binding this exciton. By the way, only and hopefully the exciton of bacteria and not of our ribosomes. And what makes the difference, in fact, is just one single H point, which is not possible to be formed in mammal ribosomes, but which is formed in the bacteria. So there's this just one H point which makes the difference between life and death. So it's quite amazing when you swallow antibiotics. So from that location, it was originally thought, well, the action of this thing is pretty simple. It's like a cork blocking here the exciton and stopping the ribosome from being able to release the protein, the mast cell protein, into the zone. But things are not that simple. It was known quite early on that this is only blocking certain sequences, not all of them. Some sequences go through, others don't, which is not really explained by such a simple picture of blocking everything. And now this cryo-EM structure by Dan Wilson in Martin's Reed actually showed now for the first time the nascent chain, and if you look closely, the green chain actually passes up to here by this erythromycin. So also here we can see it's not so easy. So we set out to look a little closer what actually is the stalling mechanism of erythromycin. There's also a nice biological background to that, which always surprises me if you think about it. So how does this thing work, and why is it there in the first place? So let me share the biology of it for a minute or so. Actually, it is a sensor which senses the antibiotics of a competing bacterium. So competing bacterium creates this antibiotics, and now our bacterium has to kind of recognize, aha, there's erythromycin around, I have to do something about it. And what it does actually is to synthesize a methyltransferase, which then modifies the excitome such that erythromycin cannot bind anymore. So that's the weapon, the drug against this erythromycin attack amongst bacteria. So that's a type of war, if you want. Now, this methyltransferase is very potent, but it has, as any drug, side effects. It reduces the overall translation rate, which you typically as a bacterium doesn't want. And so you only want to express this weapon here when erythromycin is actually there. So how do you sense that? And that's done here. So this is the sequence of the messenger RNA which synthesizes actually the leading sequence, RBL, as it is called. And it's synthesized and that's it. No problem. Whereas here, our drug, which is encoded here, is not expressed simply because the ribosome binding site is embedded in this stalk here. So hidden in the stalk, no ribosome can bind, no expression of our drug. That's the normal state. Now, as soon as some erythromycin is here, the sequence here is optimized such as to stall in the as a first sequence at all when the erythromycin binds. Very sensitive to binding. That's how the sequence is optimized. So the ribosome stops here because of this stalling. Now, for kinetic reasons, if it stops long enough, these base pairs have time enough to outcompete those which previously formed the loop hiding the ribosomal binding site here, such that the ribosomal binding site is now exposed and our drug can be released and then transcribed. So that is the mechanism how this erythromycin is sensed, quite clever, and that's the background why we got interested in that. Now let's just recall how this might work. First of all, this is the synthesis site now. That's the amino acids attached to the A site tRNA, and the cycle is that a nucleophilic attack attaches this amino acid here to the growing messenger chain. So that is the state after this synthesis step. Now, what does the erythromycin do? First impression from the structure was that this is the erythromycin. It kind of shifts the nascent chain towards the right side of the tunnel here, towards the wall of the tunnel. And the question is just, is that true? There is only this structure, there was no other structure without erythromycin available, because it doesn't stall. It's hard to get a structure if it doesn't stall. And so the first thing we did, we removed the erythromycin and checked whether it is indeed true that this nascent chain is artificially or with force pushed against this wall. And in fact, this is true. As soon as we remove the erythromycin, it goes back into a more centered position, as you can see here from the volume plots here during the simulation. Nothing happens in the presence of erythromycin, moving back in the absence. So that establishes, okay, there is a conformational transition of the nascent chain affected by the erythromycin. Now there are few escape mutations known. For example, if you mutate those residues, I mean also that one, then you recover from stalling. So how does that work? Without going into detail, that picture explains those three quite nicely because they form strong interactions to the walls, and that adds an additional barrier for further translocation and in fact perturbs the whole cycle. So that is part of the story, but it does not explain this mutant. Why does mutating this charge array actually also recover the translation of the nascent chain? And in order to study that, we looked at the left side of the wall and found that indeed, so that is now assumed into the phosphate backbone of the left side of the wall, that indeed in the presence of erythromycin in red here, that is shifted towards the left by not so much 2 angstrom, but that's enough to perturb the stereochemistry of this side if, in fact, the lysine here, the positive charge, is moved also towards the left, which makes sense. We have a negative phosphate here, positive charge here. It makes sense that the whole thing is moved towards the left, and that's indeed what the simulations also show here. This motion of the erythromycin drags with it here also the lysine, if you plot the distance between the lysine and the asp. So that's increased quite a bit and perturbed the stereochemistry. X-ray structures tell us that the unperturbed should be over there, and you'll see in the presence of erythromycin the whole distribution here of the distance moves too far away, and that would be the idea, hinder the chemical reaction necessary. Now, is that actually true? To that, we tried to also do this mutation in the simulation and mutate it away, and lo and behold, in that fact, the distribution, even in the presence of erythromycin, moves back to where it is in the absence, so that leaves the chemistry here unperturbed. And the idea also came up, if it's really a charged thing, why don't we just mutate it into a lysine? Strange enough, that hadn't been done before. So we suggested to Wilson and Martin Street to do that for us. And in fact, what he saw is that here is in fact with the arginine, not lysine, arginine, we have in fact a very, very potent blockage stalling again, which was not known before, reconfirming that these ideas again are probably true. So we have a combined mechanism. One is that the nascent chain is in fact pushed towards this wall here, forming quite a bit of interactions between the amino acids and the RNA. And the second is that in the crevice here on the left side, due to the presence of the erythromycin, this is perturbed structurally, draws with it by Coulomb interaction here charged residues and further perturbing the chemistry or stereochemistry. All right, I think I switch fast forwards if I look at the German. Yeah, 2 minutes for 30 slides might be a bit tight. So let's simply to give us also some time. One thing I wanted to share with you is disordered proteins. So disordered proteins is something which we looked into more recently. This is a disordered protein, intrinsically disordered protein, and if you look at the image, you immediately see, there is some difference between a typical PDB type folded protein and one which is much more dynamic. We got actually interested in that because in the nuclear pore complex, which is highly selective against many, many proteins, it kind of carries on the whole logistics of travel of transport between the nucleus and the cytoplasm. There is a meshwork full of disordered proteins, loop proteins they are called, and we want to learn about the selectivity. So that's what brought us into the field of disordered proteins. And in fact, we only later learned that, in fact, about a third of all proteins associated with cancer is in fact a disordered protein. So that's how we think now this gel might look like. But the point I'm trying to make here is that, watch out, we all think that for folded proteins the force fields are now quite reliable, and I think that is true. But for disordered proteins, the situation is much worse. So that is the same protein, same sequence, with this alpha force field and with this Schramm force field. And already by looking at it, you probably get a bit scared. In fact, if you change the sequence with the same force field, the difference couldn't be larger. So we looked at that a little bit more systematically. That is the histogram of radii of gyration of fully converged, I should say, that, so see the error bars, fully converged simulations, quite long ones. And these are ensemble pictures, and you can really readily see you can change the radius of gyration by a factor of 2, which is volume type, a factor of 8, just by changing the force field. So this is not really reassuring. And so we decided to work a little bit closer in it. 1 millisecond total simulation time to establish that. And now we really compare to whatever experimental data you could get a hand on, initiated also a few more collaborations, not going into that. But just what I wanted to advertise a bit is that we have modified it together with Beckman, the Charm 36 force field, to a point where we think this force field is at least now a bit more reliable also for intrinsically disordered proteins. And with that, let's skip the summary. I would like just to share you one more anecdote with Klaus. Actually, it was my first encounter with Klaus. When I was a physics student in Munich at the Technical University, I loved these things here, as many of us, I think, did. And for those who know these things, they require quite a bit of computer time. And so what I did is started at home, more or less, building what might be called my first parallel machine with this nice processor here. like 8 boards or so. And then I ran out of money. These were like 2,000 Deutschmarks for a student. Was certainly the limit. And so what I did is I just, that was the time when I had the lectures also by Klaus and Sam. And I approached a few professors, big professors at the Technical of Munich, like those guys here. Just asked them, look, I love building computers and I love physics, and why don't we strike a deal? And you pay for the hardware and I build a computer for you. Then we can do with the computer wonderful things. Maybe not only these multiple sense, but real physics. And so I got a number of replies. And this is in German, sorry, but you may probably get the gist of the idea of how these replies typically look like, depending on which region in Germany the colleagues came from. This means I don't care. And the rest you can guess. And there was only one who said, well, iron computers, that's what we need, go for it. Just go for it. And then came Helmut, some of you know, I guess, also this picture. To be a bit nasty, I had a more recent picture of him, which he looks more older than Klaus here, I guess. And then Klaus just came with this incredible amount of money, 100,000 Deutschmarks, which was maybe $100,000 now converted to today's currency, which came from the German Science Foundation, right? So I begged for a completely different purpose. And he just gave it to us. He gave us the money and said, buy your hardware, build a fast computer. And that's what we did, Helmut and myself. And the point I want to make here is really, you all know that picture, we have seen that already. It really worked, much to my surprise in retrospect. That was my first publication, maybe different from a typical publication on that. But the point I really want to make here is that in retrospect, at that time we had no idea what Klaus did here, coming freshly from school, in high school or something. With that universities, they are rich, yeah, no problem. But in retrospect, I mean, at some point Klaus would have to write a report to the German Science Foundation and say, what did you do with the money? Well, I gave it to 2 crazy students. They promised to build a computer, and of course it didn't work. Sorry. That's not a typical report you want to write. And so that is an incredible amount of trust which Klaus put into us here. And I'm still baffled by this amount of trust, which he had a good reason for it, obviously. We weren't aware of that at the time, but that worked out. And I really want to say that maybe this is one thing I can maybe hopefully contribute also to the legacy of Klaus, that trust is at the core of science. Science doesn't work without trust. If you think about it, science has advanced over the centuries tremendously. I would say also because of the trust we have into each other's work. If you measure something, I trust you. Why should I? Yeah. In politics, it's quite different. Yeah? Politics didn't advance that fast, that science. Some countries, it even got worse. So I would really like to say that this amount of trust proved that Klaus is an incredible scientist, and it's so important. With that, I would like to close saying, Klaus, I owe you a lot. Thank you.
One private science question, but so for the values you mentioned, the rotation of the lab.
That's how it looks like, yes. Yeah, exactly. Yeah, entropy is missing. Exactly. So we always we see very frequently this entropy-entropy compensation. So what we see in cases where we can calculate the free energy, you see the same thing. We have a huge enthalpy, and we have almost the same entropy, and the two cancel each other almost, and the small free energy remains. So in that sense, it is really a crude proxy to just look at the enthalpy. And there is no deeper justification than just saying, whenever we looked at it, we saw that the enthalpy does correlate roughly with the entropy. So this balancing out of two numbers, subtraction of difference of two large numbers to almost zero, doesn't produce random free energies. There seems to be a correlation. That's the only justification which I have here, and it's a rough proxy.
So, if I get it,
Thanks.
if I get it correctly, for the interdisciplinary interactions, you use the like cryo-EMF, the tRNA and mRNA map.
That's what we use to build the structures. Based on, I should add, I didn't have the time to go into that, based on express structures which we like, like the MDMFF, which we have seen before, slightly different method, to bend the structures until they optimally agree with the cryo-EMFs. Yeah.
So, basically the two interaction back and forth in
Yes.
the absence of tRNAs, right? Do you think the bridges would be different in the presence of tRNAs and in the absence? And would your model tell us about that?
Now, whether or not the two ratchet by the same amount in the absence of tRNA is actually not so well known. You need at least one tRNA bound, and then you see this ratcheting motion. And in fact, from this, again, I didn't have the time to share that, but from this analysis which we did, we in fact predicted that if you would remove one tRNA, then the angle of rotation would get even larger for that particular case. And that was subsequently measured by Holger Stark by cryo-EM. So they looked at a system where they had only one tRNA bound in the classic state, and that indeed displayed a larger mobility. So that was confirmed. It was back and forth. And that was it's all in equilibrium, so I should say here. And that was a prediction which we made, which was confirmed by cryo-EM.
Okay, so let's thank.
Thanks a lot.
Okay, so let's resume. So the next speaker is Ulrich Kleinekathofer, who comes from Jacobs University in Bremen. And the title of his talk is Molecular Level Description of Excitation Energy Transfer in Light Harvesting System.
Okay, so thanks for the nice introduction, and thanks for giving me the opportunity to be part of this nice event and to pay my tribute to Klaus. So I'm going to talk about this molecular level description of excitation and transfer, and most of you probably know that light harvesting was one of these topics that I was really interested in, and still is. I mean, the group is still working on it. And so there's this, Klaus did work on this, and it was really pioneering the field of atomistic modeling of this light harvesting system. This, for example, this paper in Physics Today, which actually you saw with the previous speaker already, which basically says how nature harvests sunlight. And so this is actually 1997, so this was already concluding on work he'd done before, so more than 20 years ago. And so there's a large variety of different protein pigment complexes, and we and others work on many different ones, but there's always you have this assembly of closely packed pigments, you have proteins around it. But how do you model this in theory? And there is always this, the problem is you're in a way in a kind of border territory. So you have to, on the one, you have the size of the system, so the system size is pretty large. And at the same time, so all of us know you can do classical MD, but that's not enough for actually describing excitation energy transfer. So you have to include somehow quantum mechanics. So somehow you have to merge these two fields, and actually don't want only to do classic static pure Menon calculation, but we really want to do dynamics of the excitation transfer in a system which at least 100,000. So this is kind of the scheme we run. We are updating this right now, but this goes back to actually a pretty 15 years old paper. So basically you start with an MD simulation. Along this MD trajectory, you do quantum chemistry, basically calculate excitation energies. Then you can easily build a time-dependent Hamiltonian, do wave propagation, and get to some observables, population transfer, time dissolved spectroscopy, all these things you can measure with the lighthouse system. Or you can calculate over time, so this is so-called spectral density, and do density matrix propagation. So this was first described in this paper, and the main author, Anna, is sitting over there. She did most of this work on this. I joined at a later stage. And how it was an interesting story how I actually first met Klaus. So in 2000, I went to a conference in Austria, and I was basically, had no clue about MD simulation. So I was basically working on this part down here, on this quantum dynamics. And so I met Klaus, and I wanted to ask him about his simulations. And it was lunchtime, he told me, why don't you join me for a bike ride? Well, most of you know, you like biking quite a bit. So we did a nice bike ride, sunshine, the clear region of Austria, suddenly thunderstorm, no tree, nothing. We got completely soaked, started hailing, it was getting a bit worse. So at some point we were finding some shelter, some barn. We were already completely soaked. There were 12 people looking at us, basically smiling because they reached the shelter before us. They were completely dry. And then it was like in a movie, a truck came by, and the water fountain in it was like this. And Klaus and I didn't care because we were already soaked, but the other two also were soaked after that. So we couldn't help and smile. And after we went back to the hotel, Klaus actually, okay, now you earn your own private lecture, and we talk all night. And then when he invited me to come here first time, that's why I started to cover. I didn't put him in 2001, and this was the first outcome. Okay, let's go a little bit into the systems. This is one of them. There's a famous story about this Fenner-Matthew-Olsen complex, because there's interesting experiments. I don't have time to go into the experimental part, but there has been interesting quantum effects found in these. Basically, there is a chlorosome with thousands of bacteriophophils. Then there is these FMO molecules which kind of work like a molecular excitonic wire, so bring the excitational reactions up. And this FMO was one of the very first crystal structures solved at all, more than 30 years ago. So it's a homotrimer. Each of them actually has 8 bacteriophophils in it, so in total you have 24 bacteriophophils. You do a simulation of it, standard simulation, room temperature, 130,000 atoms roughly. The only unusual thing we did with this kind of simulation is we stored all the atomic data basically every 2 femtoseconds, 2 to 5 femtoseconds. So not the usual 5 or 10 picoseconds, but really almost every time step. Because we really wanted to basically figure the terminal fluctuations of the complex. And then along this trajectory, you want to calculate the excitation energy. So basically, you want to know if in that moment of time the photon would come in, what is actually the energy gap of the bacteriophophil to actually excite it, and how much fluctuation is there. And if you want to do this along a trajectory, a rather long trajectory, for 24 pigments at least, you need a rather fast method. We discussed with many people, and at the end, actually, we sold it to this Zindo, this Zimmer-Berger intermediate neglect of differential orbitals. We convinced the developers of ORCA to actually fix the implementation in Zindo in their program because it wasn't working. Probably the nice thing is actually you can within these days, actually more like 5 seconds per calculation, and then you can run in a couple of days you can actually run all trajectories. And importantly, actually, you have to do a QMM calculation. It's not enough to just calculate the Beckman itself on the quantum level, but really you have to calculate, you take into account the NM charges, or the fluctuations of the environment. And what you get, so this is the kind of the fluctuation, thermal fluctuation of the bacterial profiles, and this translates into all this kind of fluctuations of the site energies. Well, this is the energy gap between ground and first excited state, and you see there's actually quite a bit of fluctuation there. So it's actually not appropriate to really just take crystal structure and do a simulation, high-level electronic structure calculation on just on one snapshot. That's what actually many people did it. And you can also see that there is no correlation in these fluctuations, so this was actually one of the things many people were advertising at some point to explain some of the experimental results, and we could actually show that this is not the case. Once you have this, basically, so this delta E, so these are the energy gaps. From the energy gap, you can calculate the energy gap out of the correlation function. This is this thing here, and then you make a half-sided Fourier transform, and you get what's called the spectral density. And in the community, so I'm a physicist by training, so in the community of physics, there's this open quantum system community which actually needs this spectral density as a key input parameter. And before we did this kind of simulations, many people were just assuming rather broad distributions, which would actually then fit some experimental results, but you can really try to calculate these. I don't want to really go into details. You can do this at different temperatures, different environments of water, glycerol water, because most of the experiments are actually done in glycerol water, and you can calculate compared to some experimental stuff. So we are not so far off. There is issues, however, with this QMM scheme. So there was a competing group from Harvard and a Supercomputing group, so we kind of leads them were faster, but then so we did charm force field and as a Zindo, and they actually did amber and DVDFT, so the black and the reds, and there's quite some difference, and we wanted to actually understand where the difference comes from. And so the question was, is it actually the quantum field, or is it the force field, and actually it's the force field. So there's quite a big difference in the force fields in amber and charm, and actually the question is if any of these force fields is really good for QMM calculations. They are both not made for QMM. But there's issues there with the force fields. Then we go to another system which is very similar in a way. So it's again a protein pigment complex. So this time it's from marine algae, and Neil Hunter had this nice slides yesterday where these belong to which classes. They don't have bacterial chlorophylls as pigments, but they have so-called bilin molecules. And for me as a physicist, the bacterial chlorophyll has this ring pi system. You basically just cut open the ring, throw away the medium, and then you have the bilin. And there are slightly different types of it called PEBs and PBBs. You can do the same thing. You set up your ND simulation, you run the quantum chemistry along this heat trajectory, and again you get heavily fluctuating site energies. Now there's two different classes of bilin molecules, and you get these differences. Now you can do something very nice in what you cannot do in an experiment. So let me go to this lower panel first. So this is this FMO, this phenol complex, which I was talking about before. So what you can do now is you can do the simulation with the QMM coupling and without the QMM coupling. So that you can actually figure out what is the influence of the environment. And for the FMO complex, if you turn off the coupling to the environment, basically the spectral density goes more or less to zero. Means there is no dephasing, no relaxation effects if you do that. So basically dephasing, relaxation effects come from coupling of the bacterial profiles to the environment, to the fluctuation of the environment. That's what you would expect. Now we do the same thing with this bilin system, this PE545 system, and now you have to compare the solid and the dashed curve. So let's look at the blue one. So the solid and the dashed one, they're almost the same. And so that means if you turn off the QMM coupling, basically there's no change. Okay, so they don't react on fluctuations of the environment. So why is that? That's very, if you really look at the overall height of these two spectral densities, they're basically the same, but they're very, the reason why they come, where they are, is very different. So we look at the highest occupied molecular orbitals and the lowest unoccupied molecular orbitals. And if you look, for example, at the PE545, the billion system, you can see basically that the spatial distribution of the HOMO and the LUMO is very similar. So what does it mean? So if you have an external charge fluctuating here, and the HOMO LUMO has roughly the same spatial distribution, they feel the same electric interaction with the fluctuations. So both levels, the ground and first excited state, go up and down more or less simultaneously. The only thing we are interested in is actually the gap. Okay, so that's why when you do this, if you do this, there is almost no influence of the fluctuating environment. If you do it with the bacterial flow, however, there's between the HOMO and the LUMO, there's a really charge redistribution, and so the fluctuating charge sees a different charge distribution of the HOMO and LUMO, and there's a drastic effect. So that's it's kind of interesting because in this field, experiments show that there are kind of long-lived quantum coherences surviving in both systems. And in the experimental papers, it always reads that it's all the same, these kind of systems are very similar. But if you look at these molecular details, the origin of the dephasing is actually very different. And what you then can do, going back, you can actually set up a Hamiltonian. Actually, you really have side energies. You can also calculate couplings. I don't go into this. You can simplest thing would be dipole-dipole coupling, but you can do better than this. When you solve the Schrödinger equation, you have to repeat this many times, averaging along different starting points of the MD trajectory to get some ensemble averaging out of this. And you get some curves like this. So basically, this tells you, let's put an excitation in one of these pigments, and let's see how fast this excitation goes to the other. So what is the decay time of going away from it? So this curves, I mean, you can see for some of them actually it goes first then to a neighboring one, and then it goes on and on. What you can see here is that there is a time scale of roughly 1 to 2 picoseconds in which this happens. Okay, so this is that's. We also just want to briefly mention. We also looked into the effect of polarization of polarized force fields, because if you want to do this QMM, this polarizable force field, so is there a big effect on the spectral densities, on the couplings? Let's focus on basically on the black and the green lines here, and this is with and without this polarization, and the effect actually is not very dramatic. For some of the pigments, the effect is a little bit larger, but overall the effect of polarization on the side energy is actually not so big. But if you start to look actually at couplings, and let's compare the lower two panels here, so this point dipole approximation for both of them would be point dipole approximation once you have a polarizer force field, and once you would do some kind of exponential screening, which people would usually do in that field. You see that, for example, this kind of screening of this difference in screening will actually lead to a factor of 2 in the couplings. Transfer rates are basically quadratic in couplings, so you're already at a factor of 4. So the polarization, it means clear that if you have two pigments, in between you have your protein, that now the polarization of that protein in between these two pigments really plays an effect. So one has to be careful with the not with the side energies, but with the couplings. Then this protein I was talking about has actually almost a twin. So I was talking about PE545, now we're talking about PE555. It's actually a very similar protein from a slightly different marine algae. It's interesting in that, so again, billion molecules as pigments, the protein environment. The interesting thing is, so if you look at the arrangement, so both are homodimers, and let's start with the PE505. So if you look at this, you have this kind of hands. So you have an arrangement that there like this, and you have a hole in the middle. And in the other case, you rotate the two trimers by 70 degrees, and they get actually a different orientation, but it's the same monomers, basically almost the same monomers, and you get these different configurations. And we actually made some detailed analysis. Is it different? Well, this is actually really looks boring. So these are the spectral densities. So how is the system coupled to the environment? They're almost the same. So the one line is the PE505, the other one is the PE555. And well, it looks boring, but it's also reassuring that our protocol we are running on a completely different protein now is actually basically giving the same results. So the protocol we have established is robust, so it's not that we repeat this formulation with a different protein, we get something very different. But because of the different orientation of these homodimers, the couplings are becoming different, so some of the pigments become closer to each other than others, and that's, well, in this case actually they get further apart. And now you can do the same thing, you can do this without the Hamiltonian, you can do the quantum dynamics, you look at the transfer time, you excite individual pigments, and you see how the excitation goes over to the other pigments. And the interesting thing is the transfer time is now something like 6 picosecond. So before it was 1 to 2, and now it's something like 4 to 6. So it's just this reorientation which changes the transfer time quite a bit. And there is then also discussions what is the relation between these different pigments. Okay, now let's come. So Neil was introducing this huge simulation, depending on how many on the details of simulation, something between 70 and 100 million atoms. And so we talked to Ali. So this is a project by Ali and Billy and many others. So one thing we always were wondering, if you do this detailed simulations you do, to get an absorption spectrum, at the very end, people always say, well, that's nice, but now we have to take care that the environment of the different rings is slightly different, so we actually add some inhomogeneous disorder, just completely empirically. And so you did all these nice simulation, and at the end you say, well, now we add something empirical. That's kind of disappointing. And now having this huge system and having more than 60 LH2 rings, you have them in different environments. So some of these LH2 rings have LH2 rings as neighbors, others have LH1 rings or F1 LPGAs as neighbors, and also this different neighborhoods will influence the energies, the side energies of the pigments, because all the electrostatic interaction with the neighbors. So we actually got 200 snapshots from this trajectory. We had to rewrite all our scripts because they were not able to handle this large data. So we had to order all the steps we did. And then what you can then actually do is extract some values for the static disorder. This is ongoing, it's not done yet. So if you, for example, there's different types of similar pigments in the rings, for this, for example, the 850 alpha, and you average it in one ring, and this is then the distribution of this side energies for these pigments in the different rings, so the 60 different rings, and you get a distribution from this. From this distribution, you can actually extract some static disorder. So this is, to my knowledge, the first time to actually try to get a handle on static disorder from atomistic simulations. Okay, otherwise, before it was always just like an add-on, and here we try to get a handle on this. And you can do this for the other types, and you always get a distribution. You can fit this as a Gaussian. This is very, and we get numbers for the Gaussian distribution, which are in the ballpark of what people usually add on empirically. So we are not. It's not that we are very far away from that. Okay, so let me go on a little bit more with the phasing. So all these in a biosystem, if you talk about quantum mechanics and biosystem, everybody will quickly tell you, oh, there's all this wiggling and there's room temperature and there's the phases will not survive very long. So the question is how long? Because of all these femtosecond experiments. There was a paper by Ulrich a couple of years ago. They did some calculation of this dephasing times based on this energy correlation function. And then I thought, well, that's actually what we did, what we have all the data available for many different systems. Why don't we actually calculate the same thing? And so you have to basically have this auto-correlation function, you have to do an interval to get the dephasing function, another interval to get the dephasing time. So that's all technical fun. So if you do that, you get this interesting plot, which is not completely surprising. So that's the average energy gap fluctuation. So that means how much fluctuation you have in the system. So if there would be no fluctuation, there would be no dephasing. So if you would be here, the dephasing would be infinite. And the stronger the energy gap fluctuation gets, you will get actually the shorter the dephasing time becomes. That's clear, that you would expect this. But what you would not expect, or what is kind of surprising, so this is all these simulations, and this is done for the individual pigments of all these simulations, you plot them from all this data, they are basically on one curve. Okay, that is kind of surprising. But this was kind of indicated by this earlier paper by Ulrich that there would be some relationship. Even more interesting is we also had this kind of time-dependent data for charge transfer systems from the group of Markus Elsner. For example, Line, cryptochrome, photolysate, and they basically also have, in this case, ionization energies along an MD trajectory. You do the same procedure, and again, you see they are pretty much on this line, so actually you get this dash line, you can explain this dash line by generalized Chipot theory, for those who know what that is. I don't have time to go into this explanation. And the solid line was actually a slight modification of this by the paper of Ulrich, so we did not do anything else than just calculate these plots and compare with these results, and actually you're right on it. So that's kind of very interesting. And for a while we were actually really wondering why we actually do get these curves. Until we realized what we have to plot is this normalized autocorrelation function, so of the energy gap. So the energy gap autocorrelation function, so this is some of the older data, we only had 5 femtosecond time steps. So these are actually 120 curves on top of each other. There's always a very fast initial decay. You get a roughly 20 femtosecond oscillation, which comes in the bacterial chlorophyll from some CO double bond stretch oscillation. And then, actually, it's interesting that the different environments actually make just a different normalization factor, but if you normalize them, they're all on top of each other. So this is kind of the fingerprint of the bacterial chlorophylls, and if you, from here, we could then actually build a theory to explain why they're all on one curve. And so it's not so surprising. You can do this for this billion system also, you get something very similar. We actually had 2 points which were not on the curves, and these are represented by the black and the red curve here, so we actually also could explain it. So that is just showing you can actually, out of this MD data and all this combination of MD quantum chemistry, you can really extract a lot of data, which also for the quantum community. Very briefly, I want to just mention that you can do very similar things in DNA. It's almost the same picture as I had before. MD simulation, quantum chemistry, in this case, with calculation ionization energies. You have to do some quantum dynamics. In this case, it's actually lots of Green's function stuff involved, and you get population transfer. But it's really from the procedure. It's very similar to what I showed before. We did this together with a group of Markus Elsner, so this is actually quantum chemistry with DFTD, so tight binding DFT. And here actually you see some spatial correlation, so let me just, okay. So again, there's an MD trajectory, so you see this wiggling, and then you see the side energies. As I said, this time it's not excitation energies, but it's ionization energies. But you get very similar behavior, but this time it's interesting that you see if you, these kind of sites, for example, the first and the second, which move as if there would be a rubber band between them, so there's kind of correlated fluctuation now. You can actually analyze and really explain this from a simulation. If you really now want to go to calculate transport to such a thing, say in a molecular wire, you would have to actually connect this to leads. You have to go through all this quantum mechanics to calculate all this. I don't want to bore you with all this. But what you really get is it's a really current through a DNA, or you can do it for any kind of other molecule in between two leads. It's highly time dependent, and you have to actually do it properly. So we actually had a couple of years back a paper on this, where we actually showed that what many people did, unfortunately, was very bad. And they spent a lot of time on the quantum chemistry, on the MD part, and then they just used Landauer for the individual snapshots, which should not be because you get completely wrong results. So you have to do actually proper time-dependent Green's functions. Otherwise, for this example, the result was off by 3 orders of magnitude. And we recently extended this work, again with a group of Markus Elsner, to actually really, so these are indicating the two goal contacts, to really get a feedback, because now if you have a charge moving, a charge also in an MD simulation, a charge really makes a difference. So what we really now do is we do a little bit of MD, calculate the side energies, look where the charges are, do a little bit of quantum dynamics, propagate the charge, and take the charge and on an average level put that charge distribution back into the MD. So really get a weak repolarization of the environment. So that's what you have to do, and actually the polarizable environment really makes a huge effect. If we really have charge transfer. For the excitation energy transfer in light harvesting system, this is not so important because it's an excitation, so you're redistributing charges. You still want to recover it's there also, but here it really has a big effect. Okay, now this was all this connection of MD with quantum chemistry. I just want to briefly say also, so the very first time, as I said, my very first visit to Obama was in 2001. I had no clue about MD simulations. And I was really astonished by what you can do. And that next year, started to learn MD, started to work on F1 APAs. And then I came back to my university, and there was this experimental colleague working on electrophysiology, and he said, "Oh, you work with Klaus, why don't you actually simulate for our systems?" And he dragged me more and more, and so Matthias Müller dragged me more and more into bacterial membrane system, and just to give you a flavor of what you're doing there, without big, large explanations, to work on translocation of antibiotics across bacterial membrane pores. So there's a ciprofloxacin going through an MC, so we do free energy calculations. Really, the students spend a lot of time to really get converged free energy surface. It's really tricky, so there's a close collaboration with pharmaceutical companies. We, for example, this is human gut bacteria. This is the so-called starch utilization system. Maybe I should actually go back. So there was a crystal structure with a peptide bound here, and if you remove the peptide, we could show that in the simulation there's a cap opening, so it's a beta barrel, there's a cap on top of it, so the substrate is bound, the cap is closed, and the crystal structure, people didn't have a clue what actually is the mechanism, so we could remove in the simulation the substrate, and we see the cap opening. So that was very nice, and actually got it nicely published. Recently, we got this maintenance of lipid asymmetry, so MLA system. So in bacteria, you have this lipopolysaccharide system, outer membrane leaflet, and you have a phospholipid membrane, and you actually have to keep that asymmetry. And we really could, so again, there was a nice new crystal structure, and you can really see if you put that protein into membrane, a water channel forming automatically, and then you can see this actually dipping into the membrane, and then actually this next step would be actually get it down there. We're working on this part right now. So there's, we would have liked to get the whole study published, but there was a very competing field, and our collaborators with crystal structure really pushed us to publish halfway, so to say. We're working on this, but all this kind of, all this is stimulated by my visits here and by all these collaborators over the years here at Beckman, and so that's always very nice to come back and to talk to people, and we have still many ongoing projects. And I've come to the end. So this is my group, a part of my group, so I really would like to thank the group here in Urbana, and all the people, many of them also in the audience, of course. So over the years, many of you actually made it also to Bremen, and we had 2 NV workshops there. We are organizing conferences on nanopores, and I think that Alec and Emma was there, some of the others were there with NV workshops. That's very nice. And all this is, of course, was triggered always by Klaus and all this enthusiasm, and this was always bringing us forward, and this is him actually giving a presentation at one of the NV workshops in Bremen. Thank you.
So the fluctuation in environment effect that you pointed out for the first system, how far does it go? I mean, you mentioned other proteins in the membrane can affect obviously lipids themselves, especially if they're charged. I can imagine do we know the lipid composition of this system or trying to compare to certain?
Well, I mean, yes, actually we with this FMO, that's why we actually tried this simulation of the FMO in water and in glycerol. And we talked to Berger in Chicago a lot about this, and after 3 hours of talking, he told us, oh, well, he has this 0.1% LDLO in there, which is a micelle former, and actually it makes the whole thing actually completely different, it's not there. But then when we did this 100 million atom system, the QMM system, so the question was, how big of a circle you have to cut out? And so that is really, I mean, actually we cut out something like 100 angstrom radius right now. Seems to be too much, but before we don't, I mean, we always see some fluctuation, we always have problems also of ions going into that radius and out, and if you don't have a radius big enough, you get artificial fluctuations from this kind of stuff. And yeah, the membrane matters, and that's why I would say it's an ongoing project. It's not finished yet.
So we mentioned that you can use NV simulation to generate trajectory in the sample to be fed into the static disorder, and you show that different pigment may have different static disorder. So I would like to know how this pigment-specific static disorder affect like energy transfer or site energy on a regular basis, like give more information without like quantitative effect.
And the thing is, when the first part I was showing you is this spectral densities, and this quantum dynamics you show is always on a rather short time scale. The excitation transfer happens in, let's say, 1-2 picoseconds or whatever. But then lipids around this pigments, they reorder on much, let's say, for example, pigment reorder on a much slower time scale. So this reordering of the environment will also change the site energies. And this we don't have in the whole procedure usually, and the environment is different for every let's say, ring. And that's why we try to get a handle on this from this huge simulation in which we have different rings and with different environments. Another option would be actually to run very long, probably coarse-grained simulations to really get the lipids rearranged a little bit, then start again, and things like that. So that's also something we have in mind to get a handle on this kind of static disorder.
Can you correlate that with something like the geometry bending of the interior core or something like that? Like the static disorder? Like, for example, if the ring is distorted, that, you know,
that is,
can you correlate the site energy with the bending?
Then we did not really look at the elasticity of the ring domain. Yeah. We didn't really look at it. So far we only looked at the site energies of the individual pigments. look at something like this, probably we should look at excitonic states. Probably. But yeah, it's
It could be, yeah, I mean, the angle between the board could be different, so that might affect the side energy.
yes, yeah. The problem is you have so many, so you have like 2,000 pigments in there, and for each of them you could do some kind of analysis. We're still kind of working on this, what is the best way how to represent this.
It should be a quick, actually.
Yeah, there should be something like that, yeah.
And welcome to the last speaker of the morning session. And the title is called Computational Microscopy of Biophysical Nanopores.
I have, as all of you speakers, too many slides. So I decided to change a little bit what I will be talking about. And really, it's going to be a story about my journey through and beyond Nanopore that hopefully will give you an appreciation of what it was to be part of Klaus's team. Alright, so I need to come clean here and start with full disclosure, and I hope this lecture is not recorded. This is how I got to Klaus's lab. I was in Tokyo and I had no idea who Klaus was. Okay. So I admit it, yeah. Alright, so what do you do? And luckily, the Google was around, and I was mixing polymers at that time, doing simulations. I didn't really want to do it. I knew that the biophysics is a cool area, so I went to Google, and this is what I did. I typed biophysics, and 9 months later, I was in Bergen. Yeah, so Klaus's website was #1 for biophysics for a long time. So when I joined Klaus's group, for a long time I would type my first name and it would be like third hit. You know, and since Alexei is a fairly popular name in Russia, so okay, so that's Urbana. This is really not really what Urbana is like. So just to make you laugh, Urbana can look much nicer. So this is the Beckman Institute, and this is the Klaus's office, right? It's an impressive building, but I'd say the most impressive part was actually inside of the building, and that was the TCBG group, or TCB group back then. So that's a snapshot from 2003. I mean, this is a picture from the website, and you can find many familiar places. So that's really the most exciting part, or valuable part of the Beckman Institute, at least to me. The group was also not without quirks, I would say, you know, and hopefully we'll show you some of them. Well, to start, there were 2 official versions of the same picture, you know, the normal one and the happy one. And that's actually how it's entered as a website, happy picture. So I leave it to you to decide which one was actually representative of what was going on in the lab. And so I'll use next 5 minutes to kind of give you my personal impression or recollection of what it was to be working in Klaus's lab. So if you think that it was about science, mostly, even you're totally mistaken. It was not really It was a little bit about science, but it was really like being part of the family. And so here's one example. This is Klaus's, one of the Klaus's favorite hands-on demonstration, the core-eye dissection. You can see at all the faces of those students at postdoc, they are frightened because they have to go and do it. This is Klaus. And here's Klaus, looking through the lens of the eye, and look at this startled picture of the pupil at the background. And here's some apprentices, and here's Klaus. Mission accomplished. He was very happy with this. This is, by the way, another relic, the haptic device. The same thing that they used to do the IMD demos was.
Do we eat lunch in those plates?
Yes.
Now you can.
All right. So the TCBG and the Beckman Institute was really full of surprises. Like you come to work and you would know what you expect. Once in a while you would get like a group of children just marching through the corridors. Some of you recognize Melech here, and occupying our 3D room. So that's pictures from the open house. I think the TAs here are more frightened than the children. And of course, we had lots of parties. So Dan and Klaus's parties were legendary. I think there were at least 2 per year, maybe more, depending on how many proposals we had to finish. So what you remember from the parties? The bratwurst, of course, the fancy wine, so I think it's actually a cider, and of course Pellegrino. And what did we have to eat? We had all kinds of things. I think Klaus's favorite was the potatoes that he made himself. I forgot the name in German. This is a fish, salmon. I had an interesting experience with this fish. I think once my group job was to deliver the fish to Klaus's fancy party. And that was not a problem. The problem was that I forgot where Klaus lived. So I was driving around urbana neighborhood, the professors get there frantically, and then finally I stopped and asked where the Schultens live, and that worked. Alright, so group jobs, they extended beyond the TCBG and even to beyond the group members. So you can see here Julio, Frank. And here's a picture. Actually, I'd like to thank Tim Skerrin for preserving those pictures. Those were happy times. So here's one thing that I want to that really startled me, and this is actually not what it looks like. No, this is just an intermediate step in realizing an ambition. Yeah. So I don't know what happened. One afternoon in March, there was a snowfall, and somehow it all clicked, and we went outside and built this sphere. So here it is. I don't know what motivated us to do this dance or something, but look at the faces. Look how connected we were. And I must say, I've never come across this kind of camaraderie, the sense of togetherness, the sense of space and purpose as in Klaus's lab, and I attribute it fully to him for being such a great leader. Alright, so that was great, but there was also science, and my first project in Klaus's lab was this. Of course, it was an amazing project, fantastic project, ATP synthase, how it works. The problem was that I was really naive. I barely could spell biophysics, and I didn't know that we didn't have a structure for it, but we did the simulations anyway. We published it. But at some point, I came to Klaus and says, Klaus, I need more papers. Okay, so can I do another project? And I had a project in mind. It was this one. So the naive idea that we will take this hexokinase enzyme and we would regulate its function by applying electric field. And Klaus listened to me. And then he said, don't worry, Alex. project for you, and it has already been funded. Okay? So that was amazing. And the project, of course, was this. And those are the 4 PIs on the original NERD grant that funded development of solid-state nanopore here in Beckman Institute. So the idea of the grant was to build a sensor of DNA sequence based on conventional silicon nanotechnology. So you would have a hole here in the transistors, and the DNA molecule would be driven through the hole in the transistor. And we hope to read the sequence of DNA just by measuring the electrical signatures, the field that the DNA molecule produced in the transistor. So that was the idea. It's very naive back then, but I had no doubt that this is gonna work. This is gonna work, so it worked. So this actual project presented a number of challenges, and those challenges kind of resulted in new technologies. So one of them, the program that they had in MD and BMD, they were not really designed to handle synthetic systems. So we had to go and build everything from scratch. So we developed atomistic models of silicon nitride membranes, methods to replicate the membranes, drill holes in them, and so on. So actually the BMD and MD programs were designed so well that they didn't have to do anything extra, it just worked just as they came. And then what do? We put the DNA strand nearby, we add water and ions as always, and then the question was, well, how do we simulate the electric field driven transport of DNA? And what we did, well, we did the simplest thing, we just applied the electric field and saw what happens. And what we found was the following. We found that the ions which were dissolved in electrolytes, they would move as prescribed by electric field. I mean, not really a big discovery, but I believe at that time we were one of the first people to measure directly the ionic current from all atom simulations. And there's a number of reasons why we could do it and others not. Well, we work with big pores and high concentration electrolytes, but nevertheless, that was the first time when we could directly relate I cannot say that it was really the first time, but we could directly relate the current that we measured in molecular dynamic simulations to the current that was measured in experiment, 1-to-1. Because the time scale of ion transport through nanopores was really nanoseconds, and all we could do was to simulate for nanoseconds. So, and then, of course, we can place the DNA molecule nearby. And here's the outcome of a months-long simulation that was run on a special queue on the MU supercomputer at Pittsburgh Supercomputer Center. So that was truly hero simulation, and at the end of the day we got this trajectory and this publication. That kind of started this field of modeling nanopore transport. Of course, Kerr also did studies of DNA transport through carbon nanotubes independently. So, alright, so that was nice, but we were not alone in the field. In fact, we were kind of latecomers. People were already thinking about using nanopores for DNA sequencing using a different technology, so-called ionic current nanopore sequencing. So, briefly speaking, so in this technology we have a membrane channel, alpha hemolysin, and a DNA molecule that will be driven through it by electric fields. So here's one of the early simulations of this process. The DNA passes through the pore, and everything happens in a system that contains solvent, so there are ions, and ions would also be driven through the pore. So positively charged ions will go up, and negatively charged ions will go down. Now, so that will contribute the ionic current. So when the pore is not occupied, you would record some level of ionic current, a steady state current, but when the DNA enters the pore, it will block the current to a certain level. And the big hope in the field was that, well, maybe one day we'll be able to use this to sequence DNA. And this is a drawing by someone with shaky hand of how the sequencing would look like. So you see there's different levels of ionic current blockades, which corresponds to different nucleotide passing through the pore. So that was the background, and well, the structure was available of the alpha hemolysin. We had lots of computer time. So one December afternoon, I put together the system and by electric field and let it run. For some time, I went on vacation. So another thing that was great about Klaus's lab, you could take time off, a lot of time off, as long as things progress. And when I came back, we had the first IV curve of the membrane channel computed just from molecular dynamics simulation. So we published this method in 2005, and now it's I would say it's one of the mainstream methods in computational characterization of ion channels. Another thing that came out from this work was the PME-Pod plugin that Jim Phillips put together. So what's interesting and surprising, so first another full disclosure, I was really skeptical when I came to Klaus's lab, this molecular dynamics simulations. I mean, how can it be accurate and so on? But this kind of, I was surprised. It was so close without without doing any kind of adjustment. It just came out right. Of course, now we know that we got lucky, but sometimes you have to get lucky. So another thing that really convinced me that the molecular dynamics work is this example that you probably heard already, but I'll bring it up anyway. So this was a challenge, a blind test given to us by experimentalists, Amit Miller and Jerome, who was a postdoc back then in Amit's lab. So they used this very clever experimental setup with the DNA hairpins, where they could control the end with which DNA would enter the channel. And the experimental observation was that once the hairpin enters the channel, the ionic current that flows through the channel depends on the orientation, and also the time it takes for the DNA to exit from the channel is also orientation dependent. So we knew the data, but we didn't actually know the answer, so we had a 25% chance of getting it right, and we got it right. That was one of the most satisfying moments from my time in Klaus's lab. So the reason was this, that when you take a DNA molecule and you confine it, then the DNA bases eventually will have to tilt, and the way they do it, they always tilt towards the 5' end. Well, not always, but they like to tilt towards the 5' end. And that creates a Christmas tree effect. If you ever try to bring Christmas trees through the door, you can definitely notice the difference. Yeah, so I was sold on nanopores, and I thought, okay, this is what I want to do. All right. So where we are, so that was back in 2005. Now let's fast forward 12 years. What happened? Well, the one thing happened is that the cost of DNA sequencing, which was a really big driver for this project, dropped by 5 orders of magnitude. I don't know if you know anything that drops so fast in price, please let me know. I think this is the record. This is the record, absolute record. So back when we started, the cost of human genome sequencing was $100 million. Now it's about $1,000. It's actually a steady number. Doesn't change much. So what else happened during this time? I've seen my own genes passing through pores. Yeah. But scientifically, the real breakthrough came when my collaborator Jens Gugler at University of Seattle, he actually sequenced DNA using nanopores. Previously there was just a cartoon. Someone would draw those steps, but no one has ever seen the steps and hit it. So the first paper came out in 2012, which was actually shown here, and there were two innovations, I would say, that made DNA sequencing with nanopore possible. Well, first of all, we've got a better pore. So this one is a so-called MSPA. It's in nature, it transports glucose, but if you engineer it a little bit, it creates a stable pore that confines only a few nucleotides. The other one is in using enzymes, such as DNA polymerase here, to control the rate with which DNA transports through the pore. So in this particular system, there is a tag of war, there's an electric field that pulls on the DNA down, and there is this pull from the polymerase that pushes DNA up. And that kind of slows it down, but of course there are artifacts because this polymerase backstabs and so on. But look at this trace. So these are the triplets of the nucleotides, TAC, 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 so that should be the same, and there is a single substitute G. Yeah? And you just basically get a different pattern of triplets. But the signal was long enough, I mean not long enough, large enough, and at the same time a company announced the first commercially available sequencer. This is Min9 from Oxford Nanopore Technologies. That was the picture that they used in the announcement. Now it looks slightly different, but still it's a palm-sized device, and full disclosure, we have a project with them, so take everything I say about the company with that in mind. But you know, it works. So DNA sequencing using nanopore is done. Yeah. But we still don't know why it works. So we have a device, it works fine, but it's not clear, because if you look at these signatures, I mean, there's no way you can tell why it should be like that. If you know current blockades for AC, G, and T, you will not be able to tell what the current for triplet is, and so on. So we were not happy about it, and that's why we used Klaus's computational microscope to figure it out, and I will just give you the punchline. So it turns out that what really determines the ionic currents through a nanopore blocked by DNA is the number of bulk-like water molecules that are in the constriction. So when the ions wants to pass through the narrow gap in the nanopore, it has to displace water. And that is a requirement. But because the space is so narrow, you really have only like 10 to 20 water molecules in the constriction, and the volume that is occupied by the water is very non-trivial. It's really like a maze, and that fact creates this nonlinear dependence of the current on the number of water molecules that gives rise to actual sequence dependence of the signal. Okay, so what else happened in the field? Of course, the graphene. Yeah, so the graphene was discovered in 2005 or 6, but the Nobel Prize was awarded in 2010. People noticed graphene because, you know, one problem was the silicon technology that we were trying to realize here in Beckman was that the silicon, you know, it's like, in comparing to the size of the DNA, I mean, it was possible to still make features of a gate, maybe like half a nanometers, but you would not actually get enough dopant in the silicons to create any signal. That's why graphene was really a game changer, and many people experimentally explored it for DNA sequencing. So here 3 groups published a paper on experimental detection of double-stranded DNA translocations through graphene nanopores. So my group also published on graphene nanopores, looking at how single-stranded DNA interacts with graphene, and the conclusion was that yes, we can sequence DNA using graphene in principle, but guess who was the first one to publish on graphene nanopores? Of course, Klaus. Klaus stayed active in this field for until the very end. So not only he published his first paper on double-strand DNA translocation through graphene nanopores, through collaboration with Jean-Pierre Lebreton, he did fantastic work on exploring different modalities of detecting DNA using electronic properties of graphene. So in this particular concept, you're looking at graphene quantum point contact transistor, where you sense the DNA, the sequence of the DNA that passes through the stacked architecture by measuring the current that flows through the graphene. Yeah. And so there's a series of papers on this subject. I'm not involved in this study, but I deeply admire this work. So what else happened in the field? I think there's really tremendous opportunities in combining plasmonics with nanopores. And this is a project that is done in my group in collaboration with Kees Dekker from TU Delft. So what is a plasmonic nanopore? It's very simple. Here's a normal pore, and here's a plasmonic pore. Normal, plasmonic. So really you need to add 2 gold bow ties and illuminate them with the laser light of the coherent frequency, so it will induce undulation of the electrons in gold. And if you choose your parameters correctly, that will focus light to a nanometer spot. So think about it as a lens, and sometimes people refer to it as plasmonic tweezers. So that's a way to focus light to the nanometer spot. And once you have something like that, you can use it just like optical tweezers. It's the same principle. With optical tweezers, you have a microscopic bead that does it. Here you just have this plasmonic thing that creates high optical intensity spot. So we set out to use it as a way to sequence DNA. I don't know if that is really now the main application of this method, but nevertheless, I think this is extremely powerful method. So what you're looking at is our schematics. So you have a bow ties. It's 2 scale. There's a pore over there. You can barely see it, and the DNA molecule that passes through. So we have a laser. Laser comes, excites, and there's a detector. So the same high intensity optical spot not only can it directly trap DNA molecule, it can also excite Raman emission. So ideally we would want to sequence the DNA, or for that matter anything, by measuring the Raman spectra of the molecule. So we wanted to simulate this, and again this is one of those things that we didn't have a recipe for. So luckily we already had the grid forces in NAMD, and we just had to couple it to continuum optics simulation that is essentially solving Maxwell equations on the grid, and then we could just use the output of a continuum optics simulations as a field that steers DNA molecules through the pore. So here's an example of, and of course we had to simulate, the gold. And guess who was the first one to simulate the gold in all atom simulations? Of course, Klaus. So this paper goes from 2010. So we actually use the force field that Klaus developed in this book. So here's typically what the simulation looks like. So in all those electric fields that drives DNA down. So what's different is the strength of the plasmonic field, and so here there are 2. So the difference is in the laser power, and those local errors that you see, that's the local forces of the plasmonic field that brings the DNA towards the bow tie. And you see that, yes, indeed, we can control the velocity of DNA transport by this plasmonic effects. And we can control it so well that we actually form like a little coil here. And this is actually not what you want if you want to sequence DNA, because that's kind of messes up all of the signals that you hope to get, because now you have a signal from a big clump. So in order to solve that, we collaborated again with Beckman, and we developed this what's 2-pore system. I mean, the idea is kind of trivial, but surprisingly, no one has thought of it before. So using 2 pores instead of one solves the translocation problem, because basically now you have equal forces, and the DNA takes a long time to exit through this pore. So I don't have time to explain what exactly we did in this work, but I think this is one of those papers that would make Klaus proud. So where are we going forward with this? So we have to insulate the 2 compartments with the nanopores, so we can apply independent potentials and wiggle the DNA back and forth. And we have to show that we can sequence DNA using SERS. How much time do we have? Alright, so just to show that it's not just some imagination, here's some experimental data. This is a design with the 2 pores, and experimentally, I mean, it's not trivial, but it's possible to manufacture those things in real life, and this is done by Becker. Okay, so in the next 7 minutes, I kind of want to tell you where we're going with this, where the field is going. So, as I said, DNA sequencing is considered to be done. Of course, there are things to improve, but scientifically, it's kind of over. There is, of course, RNA sequencing and methylation detection, so that's still on the horizon, but the really big question in the field, whether or not we can apply the same nanopore principle to sequence proteins. And of course, with proteins, it's a lot different because, and more difficult, because proteins, first of all, they are folded. Second, they don't have a uniform charge on them. And third, well, there are 20 amino acids, not counting post-translational modification, so it's a lot more complex problem. But that is the target in the nanopore field. So we recently showed that the same kind of physics that is beneficial to sequencing DNA using graphene nanopores is also beneficial to sequencing proteins. For example, proteins, they will just unfold and adhere to the surface of red graphene, and then if we adjust the pH, we can impart them with a uniform charge, and that is enough to produce stepwise unidirectional transport of peptides. Well, another alternative is to use something that people have known for a long time, the SDS-based technology. You know, once you take a protein and you boil it with SDS, well, not only you will unfold the protein, but you also will give the proteins a uniform charge, right? So here's one of the simulations that Shalini did in my labs. This is again in collaboration with Berger's lab, where we finally solved the structure of the SDS protein assembly and showed that indeed was an experiment and simulation. The complexes can be driven through the pore unidirectionally, and the signals that we obtain are indicative of the molecular weight of the protein. So we're still not there to sequence protein, but we're close. And as we were, of course, writing this paper, was the first person to study SDS. It was Klaus. 2004. So I just give you like 3 examples of what we're doing now and where we're heading. And this here really we kind of try to follow Klaus's advice to be bold. And in this example, we are demonstrating how one can use nanopore measurements to study folding of a protein. So what you're going to see is a millisecond-long simulation of the ion currents through the pore, where a protein, I believe this is a protein G, is undergoing folding-unfolding transition. So here's a full protein unfolds, and you can see a current depression in the ionic current recording. Now the protein will fall back again, and you will see the current returning to the open hole current level. So we published this year. If you are interested more in this, please talk to Wade. Wade is in the audience. But the bottom line here is nanopores can be the next single molecule instrument to study protein folding. So another area where we somehow got into it was this nuclear pore complex. So we have assembled and simulated the first all-atom model of a nuclear pore complex. It's only 140 million atoms. And we use this to simulate the ionic conductivity. The answer is 39 nanosiemens, if anyone cares, but which is actually within the range that experimentalists measure. I mean, why did we do it? I mean, nuclear pore complex is a very difficult system to study in vivo, and there is a whole field of creating artificial nuclear pore complexes where you use scaffolds like DNA origami or solid-state nanopores to immobilize different parts, and this is just the precursors to further studies. So finally, there is of course life in my group beyond nanopores. So there are 3 areas, other 3 areas that are active. Some of them Taekjip already told you about. So we are interested in modeling chromatin at all scales, starting from single base pairs to the nucleus scale. We have written our own code for it. Here again, we following Klaus's step. It's not enough to do science. We also have to provide tools to the community so other people can reproduce the result and build on it. So our tool is called ARBD. We ventured into DNA origami field, which is a fantastic field. And there our role is in providing accurate all-atom models of the DNA origami structures. We combine atomistic and multiple-level coarse-grained simulations to actually tell experimentalists what the structure looked like in solution. And the resolution of our models is actually better than the resolution of high-end cryo-EM reconstruction. Finally, we are collaborating with experimentalists in using DNA to design membrane channels. Again, if you're interested to learn more about any of those, please talk to me after my talk. So let me finish here. And so I wanted to have a slide to tell you what I learned from Klaus, but this will take me probably 10 minutes to go over it. I just want to thank Klaus for giving me a chance to realize my ambition and for showing me what a true scientist is. Thank you very much.